We assume modern cities are good at handling water. They have underground pipes, sealed roads, concrete channels, and pumping stations. On paper, water management looks solved. Yet flooded streets, damp buildings, and water damage are common problems in cities across the world. That contradiction tells us something important. The issue is not rain. The issue is how water is allowed to behave once it reaches the city. Water only causes damage when it stays longer than it should. Moving water is rarely a problem. Trapped water always is. When moisture settles into streets, walls, and foundations, it begins a slow process of decay. Stone weakens, mortar softens, wood rots, metal corrodes. None of this happens overnight, which is why it is often ignored, but it is steady and it is predictable. Modern drainage systems are designed to remove water quickly and hide it from sight. Streets are sealed to prevent absorption. Water is pushed into pipes as fast as possible. This works when systems are new and capacity is sufficient. When rainfall exceeds design limits, or when pipes clog or fail, water has nowhere to go. It spreads sideways, pulls against buildings, and stays trapped under sealed surfaces. Damage accelerates precisely because water can no longer escape naturally. Medieval cities faced the same physical forces. Rain fell without warning. Snow melted into narrow streets. Waste mixed with runoff. Buildings were tightly packed. Fire was not the only threat. Dampness was a constant danger to health, structure, and food storage. Unlike modern cities, medieval settlements had no backup systems. There were no electric pumps to recover from failure. No plastic pipes to reroute flow. Drainage had to work every day, using gravity, surface shape, and material behavior alone. This forced a different way of thinking. Medieval builders did not treat drainage as a hidden service. They treated it as a visible survival system. Water that remained in one place was considered a design failure. The goal was not to eliminate water, but to guide it continuously from where it landed to where it could leave. The real enemy was not rain. Rain has always existed. The enemy was trapped moisture. Water that entered a wall and could not dry weakened the structure. Water that pooled near foundation caused long-term settlement and cracking. Medieval builders learned this through observation over generations. They adjusted their cities accordingly. This is why medieval drainage was not based on single solutions. It was based on layered responses. Streets were shaped so water moved away from doors and walls. Channels were placed where water naturally wanted to flow. Open systems allowed problems to be seen early. Maintenance did not require specialists or machines. It required awareness and routine action. Visibility mattered. When water movement is visible, responsibility is shared. If a channel clogged, it could be cleared. If runoff collected in the wrong place, the cause could be identified. Failure did not hide underground. It appeared at the surface, where it could be corrected before causing structural damage. Modern cities often rely on sealed surfaces and centralized systems. Medieval cities relied on geometry, gravity, and redundancy. If one route failed, water found another. If rainfall increased, the system adjusted by spreading flow instead of trapping it. Drainage was not a single line of defense. It was a network. Despite modern technology, many cities still struggle with flooding and damp buildings. This is not a failure of intelligence. It is a difference in priorities. Modern systems are optimized for speed, scale, and efficiency under normal conditions. Medieval systems were optimized for resilience under variable conditions. Medieval builders had no choice but to plan for failure. Their systems had to continue working when conditions were imperfect. They learned to guide water instead of resisting it. They shaped land, streets, and buildings, so gravity did most of the work every day without intervention. Before pipes carried water underground, the ground itself was shaped to control it. Medieval cities did not begin with plumbing. They began by reshaping the ground itself. Before medieval cities built drains, they shaped the ground. This was not aesthetic choice. It was the first and most important drainage decision. Water does not need instructions. It follows gravity. Medieval builders understood this clearly, so they designed streets that quietly told water where to go. Most medieval streets were not flat. They were deliberately crowned, sloped slightly higher in the center, and lower toward the edges. This shape forced rainwater to move away from foot traffic and toward shallow channels along the sides. Even light rainfall had a direction. Even heavy rain did not sit in place for long. This mattered because standing water creates problems faster than moving water. When water stays on a street, it seeps downward. It softens the ground beneath stone paving. Over time, the surface collapses unevenly. Medieval builders avoided this by keeping streets dry as quickly as possible, using shape instead of sealed materials. Street slope also protected buildings. Doorways were rarely the lowest point on a street. Thresholds were raised slightly, and the ground immediately outside sloped away. Water reaching a building was already moving, not pooling. This reduced dampness inside walls and limited long-term moisture damage. Medieval cities also avoided straight, perfectly level streets over long distances. Small changes in elevation were intentional. They prevented water from gaining speed and eroding surfaces, while still ensuring it never stopped moving. Water that flows steadily causes less damage than water that rushes or stagnates. Paving materials played a role as well. Stone streets were often laid with small gaps between blocks. These were not construction flaws. They allowed limited absorption and slow release of water. Instead of trapping moisture under a sealed surface, the street could breathe. Water entered, moved downward, and re-emerged further along the system. In many cities, shallow side channels were carved directly into the stone paving. These channels guided water along predictable paths. Because they were visible, they could be cleared easily. Leaves, mud, and debris did not disappear underground. They accumulated where people could see them and remove them. The width of medieval streets also mattered. Narrow streets reduced the surface area exposed to rain. Less surface meant less water to manage. Where wider streets existed, slopes were more pronounced, and channels were larger. Design scaled with exposure. Modern cities often reverse this logic. Streets are flat for vehicles. Surfaces are sealed for durability. Water is expected to disappear into hidden systems immediately. When those systems fail, water has no alternative path. It spreads across flat surfaces, pulls against buildings, and enters places it should never reach. Medieval cities expected rain to stay visible. That expectation shaped every design decision. Builders assumed water would travel across the surface before leaving the city, so they focused on guiding that journey safely. This approach also simplified maintenance. A damaged slope could be repaired with stone and labour. A blocked channel could be cleared by hand. There was no dependence on specialised parts or distant supply chains. The system worked because it could be understood and fixed locally. Street shape was not a single feature. It was a continuous system repeated across the city. Every street contributed to drainage. There was no single failure point. Water moved step by step, street by street, until it reached larger channels at the city's edge. This is why medieval drainage systems aged well. They did not rely on perfection. They relied on cooperation between gravity, material, and form. When something wore down, the system still functioned. The lesson is simple. Before managing water underground, medieval cities managed it on the surface. They treated the ground itself as the first drainage tool, but streets alone were not enough. Once water reached the edges of those streets, it needed somewhere reliable to go, and that leads to the channels carved to carry water beyond the street itself. Medieval drainage worked because it was visible. Water was not hidden underground and forgotten. It was guided in the open, where its movement could be observed, corrected, and maintained. This visibility was not a limitation. It was the strength of the system. Once water left the sloped streets, it entered shallow channels designed to carry it forward. These channels were placed where water naturally wanted to flow, not where planners wished it would. Builders paid attention to runoff patterns during rain and shaped channels accordingly. The goal was not speed. The goal was consistency. Open stone channels lined the edges of streets, courtyards, and public squares. Their depth was shallow enough to prevent danger, yet deep enough to keep water contained. Because they were open, debris did not disappear silently. Leaves, dirt, and waste collected where they could be seen and removed before causing failure. This mattered because medieval cities generated constant debris. Animals moved through streets. Markets produced organic waste. Mud entered channels during storms. An underground system would have clogged quickly. Open channels allowed continuous low-effort maintenance instead of occasional large repairs. Gutters along buildings served a similar purpose. Roof water was directed into stone or wooden spouts that released water into visible paths. This prevented water from running down walls and soaking into foundations. The point of discharge was deliberate. Water was released where it could continue moving without damaging structures. Medieval builders understood something modern systems often ignore. Water that disappears too early becomes someone else's problem later. By keeping flow visible, responsibility stayed local. If a gutter broke, it was obvious. If a channel clogged, the cause was clear. Problems were solved early, not after hidden damage spread. Collection points were another key feature. Small basins or sumps were placed where multiple channels met. These slowed water slightly and allowed heavier debris to settle before flow continued. These basins were simple depressions lined with stone. They did not require precision engineering. They required access. Access was everything. A system that cannot be reached cannot be maintained. Medieval drainage systems assumed human involvement. They were built at a scale people could interact with. Clearing a channel was a routine task, not an emergency operation. Modern drainage systems aim to remove human involvement. Pipes are sealed, flow is automated. This works until it does not. When underground systems clog or collapse, the damage is sudden and expensive. Medieval systems failed gradually and visibly, giving time to respond. Open channels also handled variation better. During light rain, they carried small flows without drying out completely. During heavy rain, water spilled gently over edges into secondary paths rather than backing up violently. Overflow was expected and planned for. This reduced erosion. Water that moves slowly causes less damage than water forced through narrow pipes under pressure. Medieval channels were wide enough to lower flow speed while still maintaining direction. They worked with gravity instead of fighting it. There was also a social dimension. Because drainage channels were part of daily life, people understood their purpose. Children learned not to block them. Vendors learned where waste should not go. Maintenance was cultural, not just technical. These systems were not perfectly clean by modern standards, but they were effective. Cities remained functional. Streets dried quickly after rain. Buildings stayed structurally sound for long periods. Water left the city instead of settling inside it. The strength of medieval drainage did not come from hiding water. It came from accepting its presence and guiding it calmly. Channels, gutters, and basins formed a continuous visible network. Each part depended on the next, but none depended on technology that could not be repaired locally. As cities grew, these channels became more organized. Smaller flows fed into larger ones. Neighborhood systems connected to district routes. Everything still relied on the same principle. Water must always have somewhere to go. But guiding water across streets and through channels solved only part of the problem. Even well-drained streets mean little if buildings themselves remain damp. To truly protect a city, medieval builders had to control how water interacted with walls, courtyards, and foundations, and that required treating buildings as part of the drainage system, not separate from it. A building does not fail because it gets wet once. It fails because it never fully dries. Medieval builders understood this clearly. Their goal was not to block water completely, but to make sure it never stayed where it could cause damage. Rain hitting a roof was treated as the first moment of risk. Roofs were designed to shed water quickly and predictably. Steep pitches were common, not for appearance but for speed. Water that leaves a roof fast spends less time searching for weak points. Eaves extended beyond walls to push water away from vertical surfaces. This simple detail mattered. When rain runs down a wall, it enters joints, softens mortar, and keeps masonry damp. By throwing water outward, eaves reduced moisture exposure before it could reach the structure. Where spouts were used, they were deliberate. Water was released away from foundations, not directly at the base of walls. The discharge point was chosen so water rejoined street flow or open channels already designed to carry it onward. Roof water was never allowed to wander. Courtyards played a critical role in this system. They were not empty spaces, they were drainage buffers. Water from surrounding roofs and walls was directed inward to controlled areas where it could soak into the ground or move toward channels without threatening living spaces. Courtyard surfaces were rarely sealed. Packed earth, gravel, or permeable stone allowed water to enter slowly and leave gradually. This prevented sudden runoff while avoiding long-term saturation. The courtyard acted as a pressure release for the building. Walls themselves were designed with moisture movement in mind. Medieval masonry was not airtight. Lime mortar allowed walls to breathe. When moisture entered, it could evaporate outward instead of becoming trapped. This reduced internal dampness and limited structural weakening. Trapped moisture is more dangerous than exposure. Medieval builders avoided sealed surfaces that lock water inside walls. They accepted that water would enter occasionally. Their priority was ensuring it could always leave. Foundations followed the same logic. Buildings were often raised slightly above street level. This prevented surface water from flowing directly inside. The ground around foundations sloped away gently, encouraging water to move outward rather than settle. In many cities, narrow gaps were intentionally left between buildings and drainage paths. These were not wasted spaces. They allowed air movement and drying. Constant airflow reduced mold and rot, especially in dense urban areas. Modern construction often separates drainage from building design. Roof water is handled by pipes, walls are sealed, courtyards are minimized or paved. When moisture enters, it has fewer ways to escape. Damage accumulates silently. Medieval buildings functioned as part of the drainage system. Roofs, walls, courtyards, and foundations worked together. Water was guided from surface to surface, never forced into hidden spaces. Maintenance was simple and visible. Broken eaves were obvious. Blocked spouts could be cleared. Courtyard drainage problems appeared early. Repair did not require dismantling the building. It required observation and small corrections. This approach created durability. Buildings aged without collapsing under moisture stress. Walls dried between storms. Foundations remained stable. Structures survived not because they were impermeable, but because they were forgiving. The system accepted imperfection. Rain varied. Materials aged. Repairs happened. Design allowed for this. Medieval builders did not expect their buildings to remain unchanged. They expected them to adapt. By controlling where water landed, where it flowed, and how it left, medieval cities kept buildings dry without isolating them from their environment. Drainage was not an add-on. It was built into the architecture itself. But even well-designed buildings cannot solve the final problem alone. All that guided water still needs a destination beyond streets and walls. To finish the system, medieval cities had to move water out of the city altogether, and that required exits designed for volume, distance, and failure without collapse. Every drainage system fails if water has nowhere to go. Medieval cities understood this early. Guiding water across streets and away from buildings solved only part of the problem. The final task was removal. Water had to leave the city without backing up, eroding structures, or overwhelming any single point. Medieval cities solved this with exit routes designed for gravity, volume, and redundancy. Instead of relying on one main outlet, they built many small ones. Ditches, shallow culverts, boundary channels, and low points along city edges worked together to move water outward. City boundaries were rarely straight or sealed. They were shaped to release water naturally. Defensive ditches often doubled as drainage channels. These earthworks were not only barriers, they were collection paths that carried runoff toward fields, wetlands, or rivers beyond the settlement. This dual purpose mattered. Defensive structures were maintained regularly. By tying drainage to defense, cities ensured water routes stayed clear. Neglecting them would have weakened both protection and habitability. Culverts were used sparingly and deliberately. Where roads crossed drainage paths, stone-lined culverts allowed water to pass underneath without interruption. These culverts were short, wide, and accessible. Their design reduced pressure buildup and allowed debris to pass through instead of jamming inside. Unlike modern underground pipes, medieval culverts were not expected to hide water. They were expected to pass it calmly. If flow increased, water could spill safely over the surface instead of backing up violently. Overflow was treated as normal behavior, not failure. Many cities also used retention areas beyond their walls. Low fields, ponds, and floodplains absorbed excess water during heavy rain. These spaces were not wasted land. They protected the city by accepting water temporarily and releasing it slowly afterward. This approach spread risk. No single channel carried all the flow. No single blockage caused collapse. Water moved through a network of options, adjusting naturally to conditions. Maintenance remained simple. Ditches could be cleared with tools at hand. Culverts could be inspected visually. Sediment buildup was expected and managed routinely. There was no assumption of permanence without care. Modern drainage often aims to move water out as fast as possible through narrow systems. Medieval drainage aimed to move water out reliably through flexible ones. Speed was secondary to consistency. This difference matters. Fast systems fail suddenly. Flexible systems fail gradually. Medieval cities chose gradual failure because it allowed response. Another advantage was scale. Medieval exit routes matched the scale of rainfall and runoff. They were not oversized to handle rare extremes, nor undersized to save material. They were proportioned based on observation over time. Builders adjusted routes as the city grew, adding channels instead of replacing entire systems. Water leaving the city was treated as part of the surrounding landscape, not an external problem. Fields benefited from moisture. Wetlands filtered waste. Rivers received flow at multiple points instead of being overwhelmed at one outlet. This created balance. Cities stayed dry without exporting destruction downstream. Taken together, medieval drainage was not a collection of clever tricks. It was a complete system. Ground shape guided water. Streets moved it. Channels controlled it. Buildings shed it. Exit routes released it. No part worked alone. Each depended on the others. Failure in one area was absorbed by the rest. This is why many medieval cities remained functional for centuries. Their drainage systems were not perfect, but they were resilient. They expected variation. They allowed correction. They worked with physics instead of fighting it. Modern cities often separate drainage into specialized infrastructure. Medieval cities integrated it into daily life, architecture, and land use. Water was not hidden. It was managed openly, patiently, and logically. The lesson is not that medieval cities were superior because they were old. It is that they optimized for long-term stability instead of short-term efficiency. They accepted water as a constant presence and designed cities that could live with it. That understanding shaped streets, buildings, and landscapes into systems that quietly worked, and in many places they still do.